If you're following along the sequence of videos in Chapter 3, in this video, we are switching gears and we're going to talk about gases and how to evaluate properties associated with gases. So let's get started. So in this video, I'm going to introduce and remind you about the good feel that you probably already have for recognizing certain gases that are just commonly occurring in the world. And then, in terms of quantifying properties, going to introduce the idea of equations of state, and in particular, going to really focus on the ideal gas equation of state that we're going to use tremendously through the rest of this course. So here's it's time to shift gears a little bit if you're watching in sequence. So we've covered a good bit of material on evaluating properties for phase change substances. So I'm Xing out my bucket of water, my boiling water, my steam spewing out of the pipe. Those are that's an example of a phase change substance, H2O. And you know that there were others, right? So like propane, refrigerant. We're switching gears from that and we're going to come and talk about gases now. So, of course, it's just as much a substance. So remember, under the larger umbrella of pure substances, both these phase change substances we've talked about and now gases, they're all considered pure substances. So, of course, you've identified what we've got here. Gosh, all three of these images are for air, aren't they? A compressed air tank. We've got an atmosphere, of course, that is full of air, and a subset of the atmosphere is somebody's living room. And so these are all commonly recognized as gases. And so here, let's come up with a few more. Well, here's a fire extinguisher bottle of CO2, commonly recognized. This greenish bottle turns out to be argon that would be used in welding. Let's see, here's an interesting shape here. That would be a neon sign, and these must be helium balloons because they're floating up to the ceiling. So we know they're lighter than air. So let's come up with a reminder. Remember how we defined a state? Gosh, now I'm trying to remember if it was chapter 1 or chapter 2, but in any event, you are an expert in remembering the definition of a state. That's a condition. It's a condition of a closed or open system. And how do we define the state? We describe the state by using properties. And so the study is how do we numerically evaluate these properties? And so since we're talking about gases, let's list out, this is a screenshot from your textbook. What are some commonly recognized gases from Common Sense 101? Of course, you can just sort of breeze through this list, but I think you're gonna recognize this list as you commonly recognize them as gases here in our world, right? And how would you visualize a gas? How would you? Here's I think is a nice little image of how to imagine a gas contained in a clear Pyrex vessel with a piston and cylinder, I guess, where the molecules of the gas are all filling that cylinder. And if you squash it down, if you do work on these molecules, they're going to be closer together. They're not going to be as spread out, and they're probably going to be more active. They're probably going to be more thermally active with each other. So I think we have a pretty good physical feel for what a gas would be all about without going into the molecular details at all. We're going to treat these gases as a continuum, right? We're not digging down into the molecular behavior of gases. We're treating our closed system as a continuum. What's an equation of state? And this may be something new to you. An equation of state can be considered, it is a mathematical expression. So it is a math formula. But it relates three properties. For gases, it relates the three key critical properties: pressure, volume, and temperature. So we've got some formula that relates P, V, and T, pressure, volume, and temperature. And so for math speak, right, we could say we come up with some formula that's P is a function of T and V, or T is a function of P and V, or you see the drill, V is a function of T and P, or do you see that another way to express some of these would be F of some function of P, V, and T equals zero. So that's simply using algebra to change this formula around. So there's lots and lots of combinations associated with different candidate equations of state. And so I went to Wikipedia and typed in equations of state, and I tried to clip out a sampler of equations of state. So this top one would be, is the van der Waals equation of state. I recall my own thermodynamics student assigning us to calculate certain relationships for different equations of state and comparing numerically the numerical results of different equations of state. So that was van der Waals was one of them. The Beatty-Bridgman equation of state was another one. Okay. And then this Benedict-Webb-Rubin equation of state, I have to tell you that I am not familiar with it. Okay. And so there's constants associated with these equations of state, like A, B, et cetera, et cetera. Certainly, there are varying degrees of accuracy. However, we determine accuracy, in other words, how well is temperature predicted as a function of pressure and volume. That could be accuracy. The accuracy depends on the state of the gas, on how close it is to the critical point of the gas. You remember, so do think back about the vapor dome and labeling that critical point. Now, typically for gases, the critical point is going to be, the critical point temperature is going to be a low temperature. Okay. But we'll get into that shortly. But so do recognize that the accuracy of an equation of state depends on where the state is relative to the critical point. Another thing to recognize is this is just a sampler of three equations of state. There are many others. Many scientists have proposed various mathematical relationships between pressure, volume, and temperature of certain gases. Now I saved the best for last. This is the classic ideal gas equation of state, and you may recognize it. Now, I've stamped it important, and this equation of state applies to a closed system. Okay, so let's see, and this is widely used. This equation of state is widely used for most commonly recognized gases, and it's used very effectively and accuracy. Now, the closer the state gets to the critical point, I'm going to show you, I think, in a future video, how to check for the effectiveness of this ideal gas equation of state. We're going to enable you to check the accuracy or check how good a model of P, V, and T this equation is, depending on how far away you are from or how close you are to the critical point. Do you remember this from college chemistry? P times V equals N R bar T. PV equals N R bar T. You may or may not, but at least for right now, you're going to need to commit this to memory. P, absolute pressure. V, volume, equals N. N is the number of kilomoles in the closed system. R bar is the universal gas constant. So this R with a bar over top of it, we pronounce that R bar. And you're going to need to commit these two to memory. I believe I've got these in bigger font in a future screenshot, but also these constants are tabulated in your one-page conversion factors page as well, the universal gas constants. Okay. And then finally, temperature T is the absolute temperature, depending on the unit you're in. Okay. I'm dwelling on this because you do need to remember, you got to commit this to memory. PV equals N R bar T. That's the ideal gas equation of state. And what does it do? It relates. You see how it's a formula, and it relates pressure, volume, and temperature. So numerically, if you've got two of those values, you immediately get the third, and it's easy. It is an easy formula, much more simple than those complex Beatty-Bridgman equation, the van der Waals equation, et cetera, et cetera. So, look at that. What's R bar? Okay. Well, R bar is called the universal gas constant, and that this R with a bar over top of it is either 8.314 kilojoules per kilomole degree K or 1,545 foot-pounds force per pound mole degree R. Okay. Now R. Now I'm going to introduce a new variable called R. And R is called the gas constant, not universal. It's called the gas constant, but it's associated with each specific gas. Okay. And so here's another thing that you must commit to memory. R is simply R bar over the molecular weight of the gas you have. Okay. I think I've got some examples here in a minute, but molecular weight of many gases you should know by heart because of your passing college chemistry and remembering some key molecular weights of a handful of elements. Okay, R is R bar over the molecular weight, and so R is the gas constant for a specific gas with a molecular weight MW. Oh, here we go. So molecular weights of commonly recognized gases. It is my hope. Now, air has a molecular weight of 28.97. I strongly agree that I strongly recommend that you commit that number to your memory banks because do you see that it's the same for both systems of units? It's 28.97 kilograms per kilomole, 28.97 pounds mass per pound mole. Okay. And let's compare the air molecular weight to nitrogen. Look at that. Nitrogen, you should know by heart. It's 2 times 14 or 28. So look at, since air is mostly nitrogen and some oxygen, look how close the molecular weights are to each other. And then on and on. And so I'm going to suggest that like oxygen, 32, you should know that, 32 kilograms per kilomole, and you should not have to go to a table in the textbook to look up the molecular weight of oxygen to be, in the book, it's like 32.0005. Well, you can drop those third decimal places. 32 is going to work for us, okay? Same for nitrogen, 28, and on and on and on. So hydrogen, well, that's 2 times 1, isn't it? Or 2. All right. So you get the idea. Okay. Now what I want to do is I want to show you a true fundamental and also try to scare you away from listing out lots of formulas. Okay. Here's a statement of the ideal gas equation of state that I just showed you. P times V is equal to N R bar T. That's our starting point. But do you see also that PV equals M R T? Okay. Because N times R bar is identical to M times R because R is R bar over the molecular weight. Okay. So M over the molecular weight is the number of moles. Now, so these two top formulas, they apply to a closed system because in a closed system, your mass is fixed, isn't it? So also the moles is therefore fixed. So you've got that. So you see how these two would apply to a closed system. So if you've got and the capital V applies to a closed system, okay? These next equations, all these are identical. And so so notice how we can get from here to here by dividing both sides by M. Capital V over M is little v, okay? So this is how, and this is going to apply to either an open system or a closed system, because do you see that there's no M, there's no mass. In an open system, you don't really know what the mass is. You've got things flowing into and out of a control surface. So you don't even know what M is. You got lots of M dots, mass flow rates coming in and out. So, okay, we got that. So you see how you can derive P times little v equals RT from this. So you only have to remember this. All right. How about P is equal to rho RT? P is equal to rho RT. Well, V is 1 over rho. So that's how I can do that. I can solve for rho. Rho is P over RT. How about little v? V is, I'll start here. I'll look at this. V is RT over P. Okay, cool. Do you see what a waste it would be on if you're allowed to have a formula sheet? Look at how foolish it would be for you to write all of these down on your sheet and cost yourself lots of real estate when all you need to do is write down PV equals MRT. See how that works? And then you can get the rest from one expression. And so, of course, I think you need to remember both of these, but you can get one from the other. It does turn out that by far and away, your homework problems are going to be associated with masses and not moles. There will be a few homework problems you have with moles, but by far and away, most of your homework problems are going to be dealing with masses, because that's what we deal with when we're practicing engineering. Okay, so much for my preaching, but 1, 2, 3, 4, 5. We've got 6 formulas, but they're all a statement of the same thing: the ideal gas equation of state. Oh, the jingle, right. I got to move my little picture around. So let's look at a closed system. The jingle only applies to closed systems. It does not apply to open systems at all. And let me show you why, right? So here's my sketch. Here's my tried and true sketch of your generic closed system. Here's an ideal gas. Oh, got to be an ideal gas contained in a piston and cylinder. I'm trying to depict that we're going from state 1 to state 2. Doesn't matter if you're going up or down, just state 1 to state 2. We're adding heat, doing work. Okay. So let's see. P1V1 equals MRT1. We've got an ideal gas, so we can just plop down that relationship. P1V1 equals MRT1. Got it. Let's solve for MR equals. So let's see. MR equals P1V1 over T1. That's what M times R is. Do you see that M times R is constant for a closed system? M, constant mass. R, that's just the gas constant. R bar for the molecular weight. And we can go through the same exercise to solve. We can start with P2V2 equals MRT2, solve for MR to get P2V2 MR equals P2V2 over T2. Well, now look at this. I've got 2 expressions for MR. And so you can derive the jingle. P1V1 over T1 equals P2V2 over T2. Now that's got some power to it. I got to tell you, I've used the jingle, hundreds, if not thousands of times. But what does it apply to? What does the jingle apply to? Closed system, fixed mass, okay, and an ideal gas. And so one of the biggest pitfalls of students is they write down this jingle and then they think it applies to everything, right? Because it's so handy, right? P1V1 over T1 is P2V2 over T2. That is handy, but it doesn't apply to everything in the world. It only applies to closed system undergoing a process 1 to 2, It could be 5 to 6, et cetera, et cetera. So ideal gas, closed system, undergoing a process, 1 to 2. Ideal gas, closed system. This jingle will save your bacon on quizzes and tests, as long as you have an ideal gas and a closed system. I'm going to try to illustrate the pitfall of formulas. Let's start with the jingle. Well, it's not derived. We've derived it. P1 V1 over T1 is P2 V2 over T2. We got an ideal gas. We got a closed system. Well, let's come up with some formulas, okay? For a constant pressure process. For a constant pressure process, what's the formula? Well, let's see. I'll strike out P1 and P2, and I can use some algebra to see that V1 over V2 equals T1 over T2. That is a cool formula, isn't it? You don't need to write that down. Just write down the jingle, okay? Or a constant volume process. Well, I'll strike V1 and V2 out since they're constant, divide both sides out, and I'll come up with a handy relationship. P1 over P2 equals T1 over T2. Wow, okay. Also handy. We got a new formula. You don't need to write it down. Now, constant temperature process. This one you're going to see a lot in homework problems. A constant temperature process for a closed system and an ideal gas, constant temperature will multiply both sides by T to get P1V1 equals P2V2. Wow. So could you see that since P1V1 equals P2V2, do you see that I could also say PV equals constant? So do you see that? These are identical statements, aren't they? PV equals constant. Now think back about chapters 1 and 2, where you were given a process, a quasi-equilibrium process in which PV equaled constant. You might have had that on a quiz already. Well, do you see where we're headed, right? So for a process where PV is constant, that would be a constant temperature process only for a closed system and an ideal gas. You get it? PV is constant, so that's a kind of a cool formula, but only for closed system, ideal gas. You're gonna be able to make hay out of these things. You are really going to be able to get somewhere, but only if you try to minimize your what's the formula concept and try to focus and simplify on the basics and the fundamentals. So the jingle, really valuable, right? It's not exactly a fundamental relationship, but it is a statement of the ideal gas law for a closed system and an ideal gas. All right, frequently used equation of state. So I've repeated this from a previous slide. Really, really, really suggest you commit this to memory and some details. Let me point out some details. So PV equals MRT. That's what you're going to be using on most of your homework problems. Let's look at the pressure units. And so if you do some studying on this slide, maybe take a snapshot of it or something like that, and you start canceling units out, units. Yes, that I just was doing some checking, and I'm correct here. I was checking units on R bar of molecular weight, kilojoules per kilogram degree K. Yes. Foot-pounds force per pound mass degree R. Yes, that's correct. Absolute temperatures, always. For ideal gas relationship, always use absolute temperatures. Volume in cubic meters or cubic feet. Your pressure units in order to get your units to be consistent in the left-hand side and the right-hand side, you're going to be using units of kPa, kilonewtons per square meter, in SI, and you're going to be using pressure units in English of pounds force per square foot. Be very aware of that, okay? Not PSI, not pounds per square inch. That's kiss of death. So pounds force per square foot pressure units when using English system, kPa, or kilonewtons per square meter, when in SI, not bar. Important points to make for success in this class. So I now declare you somewhat experts in properties of ideal gases, at least the relationship between pressure, volume, and temperature properties. That helps pin down the state. Pressure, volume, and temperature. You've been exposed to it. It takes a lot of practice to really become an expert, but I'm still going to declare you an expert. What's our recap for this? It says an ideal gas is a different substance category than a phase change substance. So please recognize that. We now have two categories. An engineering decision you have to make when you read a homework problem is, do I have a phase change substance or do I have an ideal gas? All right. The next thing we covered in this video is ideal gas equation of state that you're going to use. The ideal gas equation of state that you will use in this class is PV equals mRT and or P times little v equals RT. And that applies to open or closed system, but PV equals mRT only applies to closed systems. And I hope that I haven't been too rough on you, but I've tried to give some examples to discourage you from drowning in formulas. So if you start getting formula happy, that can be the kiss of death. So want to encourage you to focus on the fundamentals and try to keep your formulas to a minimum. Okay, so that covers that. The next video is going to be yet another new idea that we want to introduce called Z, which is the compressibility factor. It has nothing to do with that Z that you saw for potential energy. It's two different animals. Z is going to be called the compressibility factor, and that is going to be a way to enable you to check gases, commonly recognized gases, as how close they are to the critical point and whether you can or cannot use the ideal gas equation of state. And it's a little bit, you're going to be using that, you're going to be getting good at it, but you're not going to be using it throughout the rest of the semester. You're going to use it and then you kind of put it away in your toolbox, potentially for later use. So I hope that helps. This was an important but short video on the ideal gas equation of state.